Good morning everyone, thanks for attending our webinar. My name is Jackie from SVG-Tech Private Limited, Singapore. We all know that almost all engineered products has to take account of the effect of fluids phenomena. From airflows through a radiator to make sure a high-performance car works as designed, to ensuring people have a persistent supply of drinking water. Understanding how the fluid will react in any given scenario has helped us understand how to engineer increasingly more efficient and sophisticated solutions to our problems. And we know there are two definite approaches to CFD. One is geometry-based, the other is systems-based. One is not better than the other. It is an unfair question. The real question is geometry against system. Modeling the system as opposed to the geometry is always quicker, and the difference in speed grows with the complexity of the system. It is very unlikely that anyone would ever model a complete system in 3D, since it would take far too long and could be so complex it may even be impossible. Simcenter Flomaster is a vertical solution for modeling thermo-fluid systems of any size and complexity, and can help companies in the energy and utility industry to face the main problems they can find. Flomaster can be used by any engineer to create the digital twin of a thermo-fluid system. This in turn allows them to make informed system design decisions early in the design process, and to reduce risks, costs, and time to market. Simcenter Flomaster helps companies to face the main challenges they have in today's highly competitive market. Time to market and cost reductions. Increased environmental awareness. Increasing regulations and warranty requirements. Increasing system complexity. Changing demographic of the employees. Recently, Aberdeen research stated that in today's highly competitive market, the window of time and opportunity to recoup development investments and bring in revenue is shrinking. This places renewed pressure to get to market as quickly as possible to maximize profitability and then be ready to follow with the next new product. Accordingly, the need to launch products quickly is the top pressure on product development. If companies fails in reducing costs and time to market, they may lose profitability and market shares to competitors. To face this challenge, companies can use system simulation to make informed decision early in the design process. Creating the digital twin of a thermo-fluid system is an easy process in Flomaster, but it can be quite time-consuming, especially for large systems. When a 3D CAD representation of the system is available, it is possible to automatically create the digital twin, thanks to the connectivity to 3D CAD. The automatic abstraction of the 3D geometry can reduce the time for creating the digital twin by up to 95%. Flomaster provides a comprehensive library that contains more than 400 ready-to-use components based on repeatable and validated experimental measures of pressure losses taken by Don Miller and his group. The direct access to the NIST RefProp database allows for easy and quick definition of fluid properties. The NIST RefProp database provides the most accurate thermo-physical property models for a variety of industry-important fluids and fluid mixtures, including accepted standards. The fast, robust, and accurate solver allows engineers to quickly and easily select and size components, and then properly balance and configure the entire system early in the design phase. As an example, in the case of multi-branched systems, engineers need to make sure that each branch has a specific fluid flow. This target is normally achieved by using regulating valves, so that when a system is built, a technician needs to be in the field to manually regulate all the valves until the desired balance is obtained. In the case of large systems with tens to perhaps hundreds of valves and branches, this may require several days of field work. Flomaster provides a specific capability called flow balancing that does exactly what its name says: it balances the system. So, what is normally done in a few days of fieldwork on the real-life system can be done in few seconds with Flomaster. And this can effectively help companies to reduce costs and time to market, as confirmed by Joe Loenders, design engineer at ZF Wind Power. Simcenter Flomaster allows for the reduction in design resources and validation effort, giving a good return on investment. The use of Simcenter Flomaster within ZF Wind Power has resulted in an efficient way of developing oil distribution networks for wind turbine gearboxes. The increasing environmental awareness together with increasing E&U costs impose to design better performing systems, or in other words, they impose companies to maximize the E&U efficiency of the systems. Oversizing components and systems is no longer possible. Optimal E&U efficiency can be achieved by quickly evaluating different designs and different operating scenarios in the framework of a parametric analysis. This in turn allows system engineers to evaluate system behavior as a function of different parameters and then to optimize the E&U efficiency. Engineers can take advantage of the speed of the solver together with an easy and quick way to set up parametric analysis, to explore the influence of different parameters on system behavior, to evaluate different designs, and to study different operating conditions. Different system configurations can be studied by applying minor changes to the baseline model. Parametric analysis can be set up in seconds, and hundreds or even thousands of simulations can run unattended in minutes. This allows engineers to quickly have a deep understanding of the system behavior. They can easily and quickly identify the parameters that have a major impact on system performance, critical operating conditions, and better design configurations. Flomaster can also be used in conjunction with process integration and design optimization tools. Thanks to the fast solver, hundreds or even thousands of simulations can be run in minutes, allowing optimizers to quickly find optimal system configurations. All of this allows engineers to not only ensure that the required performances are met, but also to design better performing systems. Flomaster allows companies to design innovative systems capable to reduce emission (HEMI), as confirmed by Sun-hee Park and Ji-woong Han from Korea Atomic Energy Research Institute. With the growing level of carbon dioxide (DK) said in the atmosphere, it is important to understand the biggest contributors and investigate options for reduction. The use of Simcenter Flomaster means KAEI can use the result as the basis for additional design considerations for their prototype generation IV sodium-cooled fast reactor. There is an increasing number of regulations for companies to comply with, plus ever tighter warranty requirements. This implies higher warranty costs and the necessity for companies to avoid in-service failures in order to avoid major damages to the company brand. It is so necessary for companies to study emergency maneuvers and failure scenarios on a digital twin. Flomaster is equipped with a highly accurate solver for transient phenomena based on the method of characteristics. The accuracy of the solver is proved by comparing the results with a number of different sources, ranging from customer and academic data to literature data, from experimental data from test rig to data computed by 3D CFD. Validation of the software is automatically run at every release to ensure quality and accuracy. And these validation reports are made available to customers. The validation of the transient solver is of particular importance when it comes to assessing compliance and safety of the system. This validation is based on experimental data available in the public literature. The demonstrated accuracy of the Flomaster transient solver allows engineers to properly model emergency maneuvers and failure scenarios on the digital twin. This, in turn, allows engineers to reduce risks associated to the project and to ensure compliance with regulations and the overall safety of the system. Simple or complex control systems controlling and driving the thermofluid systems can be directly modeled inside Flomaster or can be modeled in specialized tools like Simulink. Co-simulation can then be used to model the interaction between the control system and the thermofluid system. Flomaster provides all the tools for creating an accurate digital twin that can be used for meeting regulation requirements and for reducing the number of physical tests, as confirmed by D. Morrison and R. Illich from Airbus Operations Limited, UK. Given that refuel test rigs are expensive to develop, operate and cannot be readily modified, this test and simulation, as investigated by the use of Flomaster, means that the use of full-scale tests may be reduced. System complexity is continuously increasing. Many different systems and subsystems are present and interact with each other. This implies that complex interactions among different systems need to be taken into account in the design process and that the behavior of each system needs to be harmonized. The only way to do this is to perform system-of-system simulations using best-in-class simulation tools for each individual system and performing co-simulations capable to account for the complex interactions. The extensive collaboration with other KI tools ensures that Flomaster can fit within the company's structure and that seamless workflows can be implemented in order to perform system-of-systems simulations. The possibility to export the Flomaster model in the form of a functional mock-up unit allows performing co-simulations capable of accounting for interactions between the thermofluid system and other systems. The unique capability to leverage three-dimensional fluid dynamics within the one-dimensional simulation workflow allows extending Flomaster applicability as well as increasing the accuracy of the digital twin. This can be achieved either by using simulation-based characterization for quantifying performance data of bespoke components or by one-sim, i.e. by performing a tight fully implicit co-simulation between 1D and 3D CFD. The possibility of exporting results to pipe stress analysis tools allows to account for fluid structure interactions and to properly size the system structure. Flomaster connectivity increases collaboration among different departments and allows to define seamless workflows for accounting for system complexity. Flomaster can work together with a number of different CAE tools as confirmed by Associated Thermal and Fluid Dynamics Engineer at Mitsubishi Motors. 1D and 3D cooperative analysis approaches leading the accuracy improvements. Mitsubishi is looking into using this calculation method with design space optimization tools going forward. Another important trend that most companies need to face is the change in demographics. Experienced engineers working in the 60s and 70s are retiring. Most of the time these are the most experienced engineers. They have a great know-how of products, procedures and best practices. Also, they might have been involved in the development on in-house codes or of specialized spreadsheets used for designing and sizing systems. Most of the times their retirement means an inevitable loss of know-how for the company itself. In order to avoid this problem, companies can use commercial codes to lower the access threshold to simulation and to allow effective storage and reuse of models. This in turn allows companies to define best practices and to capture and share know-how. The intuitive, engineer-oriented interface guides the user through the modeling and analysis process. The initial launchpad allows the user to easily and quickly access all the main functionalities needed to build and analyze the digital twin of a thermofluid system. It also provides immediate access to the library of fluids and components, existing digital twins, sample systems, and extensive help and information. Sample systems in particular can be used to speed up the learning process and as a basis for building models of specific thermofluid systems. Sample systems, together with the intuitive engineer-oriented user interface, allows engineers to spend their time solving design challenges, rather than learning how to use the software. All the projects are safely stored in a relational database, allowing engineers to collaborate and share know-how. One of the main goals of Flomaster is to increase the efficiency of the simulation process, allowing users to quickly understand simulation results and take informed decisions about optimal system design. This is achieved by providing a number of effective post-processing tools. One of these is the ability to draw vectors on the schematic or to color the schematic with gradients that allows an easy visualization of the vector and scalar results, similarly to 3D CFD codes. Another tool that allows a quick understanding of system behavior is the Network Result Evaluation tool. When designing fluid systems, the designer typically has to create a system that needs to achieve several goals while working within design constraints. These constraints may include minimum and maximum flows, pressures, velocities, and temperatures. The Network Result Validation tool allows the user to define design rules that must be met, quickly check if all design rules are met, and if a design rule isn't met, to quickly find the components that don't meet the rule and investigate further. Finally, it is possible to create an Excel front-end to run Flomaster analyses in just one click. The Excel front-end can then be shared with non-expert users that can take advantage of system simulation in the familiar and safe environment of Microsoft Excel. Flomaster provides an easy-to-use interface capable to reduce the barrier to entry while increasing discoverability and the overall productivity of the company, as confirmed by Dr. Zikowski of ThyssenKrupp Marine Systems. With the Flomaster software in the SQL database, a large number of engineers can also work in parallel on a large project, improving efficiency and reducing the design cycle. Now let's look at the fluid system simulation for marine applications. The values of fluid system simulation. Firstly, for the early system development. The first step in many system designs is to get an early understanding of how the system will operate. These types of initial system development can be challenging for several reasons. First challenge with 1D modeling is that it is based on the use of empirical data to describe the behavior of the different components. Flomaster has a large database of this information already populated from the leading source for pressure loss data internal flow systems by D.S. Miller. Second, model construction is often time-consuming and prone to human errors. The data is typically already there in 3D MCAD or plant CAD systems. Simcenter Flomaster leverages this to automate model construction and significantly reduce time and effort. Third, there is a need for accurate fluid properties. With Flomaster you have several different fluids for both liquids and gases already provided and the ability to create new ones based on the NIST IEFPROP database for liquids, gases, mixtures, and two-phase. Fourth, it is often difficult to know what level of detail needs to be modeled early on. This is why Simcenter Flomaster provides sample systems of different types of fluid models to get you started faster. For the design-driven CapEx and OpEx reduction. Designs that comply with safety standards can still be highly inefficient in terms of energy consumption. Typically, pumping systems like the one shown here are prone to be over-designed, operate highly inefficiently as the loads vary. This results in high CapEx due to oversized component designs as well as high OpEx over the operating lifetime. In the given example, we start with a base case which satisfies all physical and compliance constraints with temperatures, pressures, and flow velocities within acceptable ranges. This is then linked to a spreadsheet with cost data based on typical industrial values. A quick cost estimation for an 8-year, 10 hours per day operating life cycle demonstrates fairly high costs, particularly those for energy consumed for running the pumps. The Flomaster model and cost sheet are then put in HEEDs to optimize total costs by changing the following design parameters: pipe diameters, heat exchanger tube lengths, pump capacities with one pump, pump capacities and with two pumps in parallel. Successive optimization runs in HEEDs reveals that design with two pumps in parallel would be the best from a cost point of view for the entire life cycle despite higher maintenance and upfront CapEx. This design, which is feasible obeying all physical constraints, reduces expenditure by about $200,000 over the operating life cycle. For optimizing dynamic operation, slowdown and tripping factors are introduced for the pumps for emission profile for load variation for a typical day are applied to the model, which delivers further reduction in operating costs and better energy performance. Solution and benefits. Simcenter Flomaster allows detailed physical modeling of such systems. These physical models can be integrated with cost data in Simcenter HEEDs, which has a state-of-the-art optimization function built in to explore the design space for improved designs from a total costs perspective that are feasible and do not violate any physical constraints. An improved feasible design delivers a direct reduction in CapEx and OpEx. For dynamic loading, we can further introduce slowdown or tripping factors which can reduce pump speeds or completely trip one of the pumps in operation when the load falls below a threshold. This can lead to further OpEx reductions and can be applied to existing designs to improve operational efficiencies. For hydraulic and thermal safety. Moving heat effectively across large systems with appropriate flow distribution, ensuring no hotspots, bottlenecks are formed, as these can have dire consequences. Solution. Simcenter Flomaster offers validated pressure loss data in 400+ ready-to-use components. This information is helpful in sizing lines for required flow distribution and pump selection early in the design phase. The same system design can then be analyzed for multiple steady and transient scenarios. Benefits. Highly accurate loss data bridges information data availability gaps. The same model allows seamless workflow from design to analysis and failure investigation. Application description. The given example models a closed-loop heating water network where the water is heated up near the storage and pumping station and the heated water is then circulated throughout the entire vessel. The steps to design such networks typically follow the order as below. Ensuring appropriate flow distribution. Effective pipe diameter selection on systems pressure resistance and pump operation. Steady-state scenario variation, flow prediction, are required valve settings under multiple steady operating conditions. Transient water hammer cavitation, pump and valve regulation. Transient with heat transfer, temperature distribution and evolution. This allows different analyses from design to troubleshooting to be completed exhaustively with one single model in a single environment. For integration with 3D CFD and control systems. As complexity of systems increases, there is a need to integrate multiple subsystems seamlessly. Solution and benefits. The Simcenter AIMSIM platform creates the foundation for an ecosystem where we can perform co-simulation and share simulation models in an efficient and secure way to facilitate building of digital twin. Such platform is used to solve challenges with designing, building, integrating, commissioning and operating complex, integrated systems. AIMSIM offers seamless integration of other Simcenter tools which are state-of-the-art in their domain, like in the given case Flomaster for thermofluids, Star CCM Plus for hydrodynamics, and quick import of fluid networks from native MCAD, Solid Edge, NX or Plant CAD isometrics *.pcf or *.idf to 1D models. This enables creation of a transparent, manageable and robust digital twin which assesses different mission profiles in terms of performances, fuel consumption and pollutant emissions. Benefit: faster, better performing product, improved collaboration between yards and suppliers, highly integrated systems. Let's look at the typical application examples. As a competitive edge, once a model is created, there is a smooth workflow starting from static, line sizing, scenario analyses and extending to dynamic analysis with heat transfer and hydrodynamic force calculations. The fast, robust and accurate solver allows engineers to quickly and easily select and size components, and then properly balance and configure the entire system early in the design phase. As an example, in the case of multi-branched systems, engineers need to make sure that each branch has a specific fluid flow. This target is normally achieved by using regulating valves, so that when a system is built, a technician needs to be in the field to manually regulate all the valves until the desired balance is obtained. In the case of large systems with tens to perhaps hundreds of valves and branches, this may require several days of fieldwork. Flomaster provides a specific capability called flow balancing that does exactly what its name says: it balances the system. So, what is normally done in a few days of fieldwork on the real-life system can be done in few seconds on the digital twin. When designing auxiliary systems, there are several steps that need to be explored, including doing initial estimates early in the design, sizing components for efficient flow distribution, investigating emergency shutdown and thermal failure scenarios, and ensuring the design is safe from cavitation and allows uniform and quick transport of heat-carrying fluids. Behavior of fluid systems during maneuvers is difficult to predict as relative positions change in time, impacting hydrostatic heads across the frame. Now let's look at the oil and gas and process plant applications. Offshore, subsea hydraulics, FPSO platforms, fire protection, trim ballast, cooling systems, injection system, pipelines, transmission lines, gathering systems, distribution systems, auxiliary systems, purge facilities, compressor stations, pumping stations, loading, unloading, tank farms. The first application we can take a look at is for cooling systems. These systems are found most commonly on drilling platforms and FPSOs. They are usually single-phase and are used to extract heat from different parts of the system. This makes these systems one of the most popular areas of Flomaster use. Flomaster is an excellent solution for this application because it provides a variety of different heat exchanges, multiple pipe options, 2 different thermal solvers, and an established fluid property database means even the most complex systems can be analyzed for efficiency. Another area of application for Flomaster is in the safety systems such as fire suppression. When working on a drilling platform or FPSO, the ability to handle a fire is critical. These systems are usually significant distance from any help, and so the necessity for them to suppress the fire is paramount. Flomaster provides an ideal solution with the ability to size delivery lines to balance required flows and understand fill times for dry systems before the system is ever needed. Another important application for Flomaster is injection systems, commonly water injection systems. As we discussed earlier, cost is a major driver for the oil and gas companies, and since the number of known wells is shrinking, it is becoming more and more expensive to find, drill, and begin extracting. For this reason, it is important to get the most out of every possible well, especially when dealing with subsea wells which can cost upwards of $100 million to get up and running. With these systems, it is very important to control the amount of water injected into the well to ensure proper production, but it is also important to ensure safe operation even during emergency shutdown. Flomaster provides an analysis tool that quickly helps determine proper valve position to regulate flow with flow balancing, and can also be used for dangerous pressure surge studies during emergency shutdown. Another area of use for Flomaster is in pipelines. Transmission pipelines can run for thousands of miles, and during that time they can run over mountains, undersea, and across plains. This results in the need to account for significant differences in elevation, as well as changes to external conditions such as heat transfer. There is also the concern of multiple pipelines coming together in what are called gathering systems. Being able to handle the differences between these branched streams in the same tool can be very important. Flomaster is a system-level analysis tool that easily accounts for the profile of the pipeline with complex heat transfer options for both single and branched networks. When looking at compressor stations, engineers need to ensure efficient operation under a myriad of operating conditions. If the pipelines act as the veins of a natural gas system, the compressor station acts as the heart. It is critical that it is designed to ensure minimal pressure loss from the compressor to the pipeline so that the gas can reach its destination, while also being prepared to run under different conditions such as startup and shutdown for seasonal requirements. Luckily, Flomaster is a flexible tool that provides accurate loss data for minimizing system loss through complicated pipe systems while allowing for quick what-if-batch analysis. Along with safety system design, engineers need to ensure that the system will operate as smoothly and efficiently as possible. Making sure the system is running at maximum efficiency and never goes out of service unexpectedly can have a huge effect on the profitability of a plant. As such, making sure that raw materials can reach the important parts of the process in cost-effective manner while ensuring that the chance for water hammer is minimized is very important. As with the delivery of the final product, many times this product will be sent off to holding tanks or even transportation vessels such as trucks, trains, or ships. These systems will need to handle abrupt changes and rapid valve closure. Again, Flomaster is an ideal solution as an industry-leading rapid transient solver for analyzing pressure surge scenarios with variable parameters to understand the effect design changes fast. Another area of safety concern is pressure relief systems. If gases are allowed to build up to extreme pressures, it can jeopardize the integrity of the systems, possibly having explosive results. Engineers need to ensure that these systems can operate under safe pressures and that if overpressurization starts to occur, they have designed relief systems that can adequately relieve the pressure. That's why Flomaster provides an excellent solution as an analysis tool that accurately simulates the complex transient behavior of gases even as it approaches critical temperature and pressures with high Mach numbers. That's all for today's webinar. Feel free to drop me an email if you have any questions. Thank you.